We look up at the stars and dream of meeting alien civilizations. Fleets of starships crossing the galaxy like ships across an ocean. First contact at the edge of our solar system. A signal in the night decoded after 100 years. The reality is much more frightening. The space between the stars is not a bridge. It is a dead zone. A desert of radiation. Absolute cold and distances that human biology cannot survive and human imagination cannot accurately picture. Today we walk through why, even if the universe is full of life, we are statistically condemned to never meet any of it. And the reason is not our technology. The reason is the fundamental laws of physics themselves. Three categories of obstacles stand between humanity and any other civilization in the galaxy. Each one alone would be enough to make contact nearly impossible. Together, they make it a mathematical certainty that we will spend our entire existence as a species shouting into a void that cannot answer back in time. Most people picture interstellar space as empty, a perfect vacuum, nothing between you and the destination but darkness. This is wrong. The space between the stars in our galactic neighborhood, called the local interstellar cloud, contains roughly 1.8 hydrogen atoms per cubic centimeter. By terrestrial standards, that is essentially nothing. The best laboratory vacuum chambers on Earth can only achieve about 1,000,000 times that density. Interstellar space is technically a better vacuum than any human technology can produce. And yet those 1.8 atoms per cubic centimeter become a problem the moment you try to travel fast through them. If a spacecraft is moving at 30% of the speed of light, every hydrogen atom in its path arrives with kinetic energy comparable to particles inside a nuclear research accelerator. At 50% of the speed of light, each atom hits with over 100 million electron volts of energy. That is the same energy used in medical proton therapy beams to destroy cancer cells. Except instead of one targeted beam, your spacecraft is being bombarded by a continuous storm of these particles, hitting every square centimeter of its leading edge, several thousand atoms per second per square centimeter for years on end. What happens to a biological crew exposed to that? Their tissues are torn apart at the molecular level. Their DNA fragments, their organs fail. Even a few minutes of unshielded exposure to relativistic interstellar gas would deliver a radiation dose hundreds of times higher than any lethal limit ever recorded for human exposure. There is no human shielding strategy that solves this without making the spacecraft so heavy it cannot accelerate to relativistic speeds in the first place. This is not a problem of building better suits. It is not a problem of finding more powerful engines. It is a hard physical limit written into the geometry of how matter and energy interact at high velocity. To cross interstellar distances within a human lifetime, you have to travel close to the speed of light. And the moment you travel close to the speed of light, the empty desert between the stars turns into a continuous nuclear storm that no biological crew could survive. The same problem applies to electronics. Modern radiation-hardened computer chips can survive in low Earth orbit for years. They cannot survive a relativistic interstellar transit. Studies estimate that unshielded electronic components on a starship moving above 0.3 of the speed of light would degrade to inoperable conditions in minutes. Not years, minutes. The chips fail before the ship has moved meaningfully closer to its destination. Suppose for a moment that we somehow solve the radiation problem from part 1. We invent perfect shielding. We build engines that can push a spacecraft to a useful fraction of the speed of light without killing the passengers. We still cannot reach most of the universe. The reason is something Edwin Hubble discovered in 1929 and Saul Perlmutter, Brian Schmidt, and Adam Rees refined in 1988. Space itself is expanding, and not just expanding, accelerating in its expansion. The universe is roughly 93 billion light-years across in observable diameter. That number is growing every second. Galaxies that are far enough away from us are moving away faster than the speed of light, not because they are physically traveling that fast, but because the space between them and us is stretching at that rate. Nothing can catch them. Even a beam of light fired in their direction today would never reach them, because space is expanding faster than the light can cross it. Astronomers call this the cosmic event horizon. It is a real, measurable boundary. Anything past it, in a physical sense, lost to us forever. We can still see the light from those galaxies because that light was emitted billions of years ago when the galaxies were much closer. But the galaxies themselves in their current state are unreachable, beyond the horizon. How much of the universe is reachable from where we are? Recent calculations put it at roughly 6%. 6% of the observable universe is in principle reachable by a spacecraft traveling at the speed of light given infinite time. The other 94% is permanently beyond reach. Within our own galaxy, things are still bad. The Milky Way is about 100,000 light-years across. A signal sent from the far side of our galaxy to Earth takes that long to arrive. By the time it gets here, the civilization that sent it could have already risen and fallen multiple times. So even if alien civilizations exist in vast numbers scattered across the cosmos, the simple geometry of an expanding universe places hard physical walls between them. Most of those civilizations are, by definition, unreachable, no matter how advanced they get. And there is one more obstacle the expanding universe creates, which is even more devastating than distance itself. Because two civilizations meeting in space requires more than just being close enough geographically. They have to exist at the same time, and the timeline of the universe makes that nearly impossible. Now we get to the part of the problem nobody wants to talk about. To meet aliens, we do not just have to be close enough in space. We have to be close enough in time. And the timescales involved make that almost mathematically impossible. The Milky Way galaxy is approximately 13.6 billion years old. Stars have been forming, dying, and forming new generations across that entire span. Habitable planets have probably been emerging on and off for at least 10 billion years. Civilizations, if they arise on those planets, could have been rising and falling that entire time. Human technological civilization, by contrast, is about 100 years old. Our first radio transmissions, powerful enough to leak into space, happened in the 1920s. Our oldest active civilization, depending on how you count it, is maybe 10,000 years old. If you stretch the entire age of the galaxy across a single year on a calendar, the entire history of human technology fits inside the last quarter of a second of December 31st. We are a flicker, a spark, and every other civilization that has ever existed in this galaxy was probably also a spark at some other moment in those 13.6 billion years. For two civilizations to meet, their flickers have to overlap. Right now, in this brief window, we have to be transmitting and they have to be transmitting, and the signals have to cover the distance between us, and we have to be looking in the right direction with the right equipment when their signal arrives. Statistical models of the galaxy estimate that even if civilizations are common, the typical lifespan of a technologically active civilization may only be a few thousand years. After that, civilizations either destroy themselves, transition to a non-detectable state, or simply lose interest in broadcasting their existence to the cosmos. That gives a very narrow window for any two civilizations to be simultaneously broadcasting. The radio signals we sent in the 1920s are now 100 light-years away. Any civilization within that distance has, in principle, had time to detect them. There are about 15,000 stars within 100 light-years of Earth. Even if one of them harbored an actively broadcasting civilization, we should already be hearing them. We're not. The silence is real, and it has a name: the Fermi paradox. Civilizations may rise and fall like sparks in the dark, scattered across a galaxy 100,000 light-years wide and 13.6 billion years old. The probability of any two sparks happening to be lit at the same moment, close enough together with the right tools to see each other, is small, possibly very small. The silence of the universe is not necessarily proof that nobody is out there. It may simply be proof that everyone out there is on a different schedule. By now you can see the structure of the problem: 3 independent walls. The first is physical. Interstellar gas turns into nuclear radiation at relativistic speeds, killing any biological crew that tries to cross. The second is cosmological. The universe is expanding faster than light beyond a certain horizon, putting most of it permanently out of reach. The third is temporal. Civilizations are short-lived sparks in a galaxy that is 13.6 billion years old, and the chance of any two sparks overlapping in time and space is statistically small. Each wall alone would make contact extremely difficult. Together they would form what could be called the distance paradox. Even if alien life is common in the universe, we are essentially guaranteed never to meet any of it. Now, every time someone makes this argument on YouTube, the comment section fills up with two specific objections. Let's deal with both. Objection 1. Warp drives. The fictional Star Trek concept of warping space to travel faster than light has a real mathematical foundation. In 1994, the physicist Miguel Alcubierre showed that Einstein's equations of general relativity allow a solution where space contracts in front of a spacecraft and expands behind it, effectively letting the ship cross enormous distances without exceeding the speed of light locally. The math works. The physics, however, requires something called negative energy density, a form of matter that has never been observed to exist, that we don't know how to produce, and that our best theories suggest may not be physically possible to create in the quantities required. The energy needed for an Alcubierre drive, even with optimistic estimates, is roughly equivalent to the total mass energy of Jupiter. As of 2026, no laboratory anywhere has produced even a milligram of usable negative energy. The drive is mathematics, not engineering. Objection 2. Wormholes. Same problem. General relativity allows for solutions called Einstein-Rosen bridges, where two distant regions of space are connected through a shortcut. Mathematically valid, physically the wormhole would collapse the moment anything tried to pass through it, unless held open by the same kind of exotic matter that warp drives need. We do not have it. We don't know how to make it, and we're not even sure it can exist. These are not impossible problems forever. They are impossible problems with current physics. New physics may someday rewrite the rules, but pretending the rewrite is imminent or even likely within the next century is wishful thinking dressed up as optimism. Which leaves us with a possibility worth considering. Maybe the silence of the universe is not a tragedy. Maybe it is a feature. If interstellar contact were trivially easy, every civilization that ever rose to technological capability would be exposed immediately to every other civilization in its neighborhood. Some of those civilizations would be friendly, some would not. The walls of physics that prevent contact also prevent invasion, exploitation, and any of the darker outcomes that a galaxy of contactable species might produce. Three walls of physics keep us isolated. Maybe they are also the reason we have been allowed to develop in peace on a single small planet without anyone ever showing up to tell us what to do. We get to figure out who we are first, before any external civilization gets a vote in the matter. The conclusion is unsettling, but it does not have to be hopeless. We will probably never meet aliens face to face, not because they do not exist. Probably they do. The galaxy is too vast, the number of habitable worlds too high, the chemistry of life too plausible for Earth to be the only place where complex biology has ever appeared. The conclusion of mainstream astrobiology is that we are almost certainly not alone in the universe. But not being alone is not the same as being able to meet. The walls between us and any other civilization are not engineering problems waiting to be solved. They are the architecture of the universe itself. And no amount of technological progress is going to change the speed of light, the size of the cosmos, or the ages at which different civilizations rise and fall. What we can do is talk to ourselves. We can build telescopes that look at the chemistry of distant atmospheres and detect the chemical fingerprints of life from light years away. We can listen for radio signals that may have been broadcast millions of years ago. We can send our own signals into the void, knowing that any answer will arrive in a future where we may no longer exist. The conversation, if there is one, will be ancient, slow, asynchronous. It won't be Star Trek. It won't be Independence Day. It'll be a kind of correspondence by mail, except the Postal Service is the speed of light and the recipient may be a civilization that has been extinct for 1,000 years. And maybe that is enough. Maybe knowing that we are not alone, even if we cannot reach the others, is itself the deepest discovery we are ever going to make. Now you know why we will probably never meet aliens. But there are two human-built objects that are right now drifting through interstellar space, beyond the heliopause, recording what is actually out there. The Voyagers. And what they are finding past the boundary of our solar system is stranger than the textbooks ever predicted. Watch Beyond the Heliopause, what the Voyager probes will really find in deep interstellar space, to find out.